Hi, everyone. This is the slides for geometry, Platonic Esoteric Geometry at the Platonic Academy of Melbourne, week 4, autumn 2021. And I'll call these set of slides Final Square Dance, our last chance to look at the square and the diagonal of the square before we move on. Okay, so I'll just take you through the slides that we did last night, and we'll just so you can remember all that stuff. Okay, so here we go. So we'll remember that we've had our unit square, our monad square, and we thought about how we might double that square, solve the problem of the doubling of the square. So the solution was to draw a square on the diagonal. And we can see just by inspection that this second square on the diagonal, is double the first square. Just by, if you like, counting those triangles, realizing that each triangle is half the original square, and there's 2 of those triangles in the original square, and then there's 4 triangles in the second square. All right. So, and I've just colored those in there, and we call it the unit square. We always tend to start with our first line we draw as unit or 1, no matter how long it is, how many centimeters or inches or whatever measure you use. The first line will be 1, and the first square therefore is 1. It was later called the monad square, monad being the original unity out of which things emerge. Okay, so that's 1, area of 1, and then an area of 2. So we know that because it's double. Okay, and we can also extend our diagram to include the special case of Pythagoras' theorem, where the squares on the side equal the squares on the diagonal. So again, we can see that by counting. We count that each of the squares on the sides has 2 triangles, 1, 2, 1, 2, and the square on the diagonal has 4 triangles, and so is double. Okay, and so that is Pythagoras' theorem as applied to the square. And of course, the diagonal is often called, when you hear Pythagoras' theorem, it's referred to in terms of a right-angled triangle. So this dark triangle here, and that's the square on the hypotenuse. Okay. So we've got those areas designated according to our rules. Now let's consider the sides. Remember, we call the sides the roots. So there's this idea that of root and power. So you have a line, and the line has the power to create the square in this case. And so you have the root of 1, and its power is the area 1. So then we can consider, well, what if the power is 2? What is the root of that second double square? Well, it's root 2, isn't it? Now, if we look at root 1, square root of the area 1 is 1, because 1 times 1 equals 1. So that's usually how we calculate this, the area of a square. So 1 times 1 equals 1. But what is root 2? Well, actually, root 2 cannot be expressed precisely as a number. So it can't be expressed as a ratio. It is a ratio, a geometric ratio. We can draw it in here exactly. It's the diagonal of the unit square, but it can't be expressed as a numerical ratio. So we can express it approximately, and when we do it in decimal counting, the decimals just keep going on and on. So we can approximate it as 1.4, 1.41 often, or 1.4142, 13562, and so on and so on. It never actually gets to a precise ratio, or if you like, numerical expression, a precise numerical ratio, because it is a precise geometric ratio here. Okay, but we just have to call it root 2, and that's okay, because if we just keep building in the same ratio, we're starting off with that 1 and we're building that diagonal, and we keep building, as we'll see, we don't really need to have a precise expression as numbers. And so that's staying in the geometry. And you can imagine when you're building a structure like a cathedral or something else like that, if you stay in the same ratios, you don't necessarily have to go to a numerical expression in order to design your structure. So let's do that. Let's start putting in some of the other numbers here. Now we've got the question marks there. What is that diagonal of the second square? Well, if we look down below, we can see that one of those lines is the side of the original square. So that's 1. And we can see by inspection that that is equal to the line on the other side. So we can see that the length of that line there in the second square is 1 + 1 = 2. Okay. Now, let's build this. I've just made it a bit smaller there so we can build a bit and have a look at what happens after that. So we've built our square on the diagonal. We've got our double square, and now we're building a square on that diagonal. Okay, and that square, as we worked out, is 1 + 1 = 2 for its side. So we can work out from that the area of the third square. So we're doing a repeated process here, where we do the same process on the product of the process. So we've got our original square, we draw a square on the diagonal, and so that generates a new square, and then we draw a square on that diagonal. So the process is repeated on the product. This often happens in this sort of geometry. It's where the generation occurs by ratio or logos. Okay, so we've got that square there, and we've got the double series. And the double series we can see continuing here if we extend it a bit more on this new diagram, where we've gone from 1, the original area, to 2, to 4, and then this new square here is 8, area of 8. So double, double, double. And remember, these areas are the powers, and so, or dynamis, the old Greek. And so that gives us the geometric series of double. Now, remember, a geometric series is, or geometric progression is analogia in the old Greek, and it's referring to the continuous application of a ratio. So you think of this as a growth by ratio. So we have 1 double is 2, double is 4, double is 8, double is 16, and so on, applying the same process, the same ratio all the way along, and we get that series. Now, of course, geometric progression could be by double, but it also could be by triple, or it could be by half, or it could be by 1.5, or by 10, or by 100, or whatever else. So long as the same ratio is applied each time, then it is what we call these days a geometric progression, or in the old days, an analogia. Okay, now let's look at the sides. So we'll start down here with the side of the monad square, which is 1. And then the new side, the side on the diagonal, is root 2. And then the next side is on that diagonal is 2. And then the next one, you can see how, and you can probably look at this later, why that is 2 root 2, because it's double the size of the second square. And then the next one, you can see, if you look at it later, why the next side is 4. So this is interesting progression, and we'll see why this is interesting. One of the reasons why this is interesting later. So we've got the power series, which is double, but the root series is double, but with something in between. Okay, so it goes from 1 to root 2 to 2 to 2 root 2 to 4. And each time here, it's multiplied, not double or triple or 1.5 or anything, it's by root 2. So 1 by root 2 is root 2. And then root 2 by root 2 is 2. Remember, that gives you the area of the second square, but we're talking about sides here. So 2 by root 2 is 2 root 2. 2 root 2 by root 2 is 4. Okay. And then it just keeps going up in that ratio. So the roots go at kind of half the pace, if you like, half the rate of change in this series. Okay. So now remember, we considered last time the first 3 in the series actually condensed into one. Okay, so this square here that I've just put on top of the other diagram is the first 2 squares down here, and then the hidden 4 square, which we've just drawn on top of there. Okay, so we can see the 3 in 1. We've got the original monad square, and then we've got the square on the diagonal, which is the double square. And then now this is where it's slightly different in the condensing. We see how the diagonal on the second square is the same as the side on the third square. It's the same length. And so the 4 square is just drawn on top of the third square. So this is actually the diagram that was drawn in Plato's memo. So I hope I didn't mislead you there. This is the diagram that was drawn in the sand in the description in the memo. So the first 3 in the series given as this one condensed diagram. And this is an important image. This is important presentation, as we shall see when we look at the relationship between circles and squares. So this is an important thing, because these are 2 in geometry, in thinking about space. Anyway, the circle and the square are 2 fundamental shapes. And you can think about why that is. It's quite profound, actually, if you think about it. And we will be thinking about this as we go through. Now, we're not going to do much with circles, mostly in relation to squares, and therefore not very much about pi, the ratio pi. But here, if we might remember, if we don't remember, that's okay, that pi is the ratio of the diagonal, the diameter of the circle, the ratio of the diameter of the circle to the circumference, right? So remember, the diameter is not like we're working with radiuses with the compass all the time, right? So radius is half the diameter. It's like the spokes on a wheel, the radius. But the diameter is the full length across the circle, across the greater expanse of the circle, one side to the other. And notice how in this diagram, the diameter is equal to the square drawn around the circle. So that if the diameter is 1, then the circumference of the circle, the green circumference of the circle there, is pi, okay? Because the ratio between the diameter and the circumference is pi. Now, pi is approximately 3. So if you bent this square sides, if it was a piece of wire or something, and you bent it around, 3 of the sides of the square would almost make the circle. So 3 instead of 4 would make the circle. And we might remember that if you are more precise in the numerical approximation of this ratio, it's like 3.14 and so on and so on. Another irrational in the sense that the ratio that is very real here and is very precise here, this ratio can't be expressed as a numerical ratio. Okay, but it can be expressed in the geometry itself, and we can keep working with it. We don't need to introduce numerical approximations when we're staying in the geometry. So what we've got here is the one is both the side of the monad square we've got here, and if you like the monad circle as well, it is its diameter. And so the circumference of the circle drawn inside the square is pi, and the square's diagonal, of course, is √2, as we've been seeing. All right, so we can build out from this, and the one way we can build out is by building circles around squares and squares around circles, which gives interesting geometric series, which are on the right of our screen there. But let's just look at this slowly. So we've gone, the important thing to notice here is that the diagonal of the square drawn inside a circle, so we look at the outer circle here, and we're now talking about the square as being drawn inside, inscribed inside that circle, right, touching it with its corners. This time the diameter of this circle is √2, right? So let's look at that. So here we've got the diameter of the circle drawn inside is 1, and where the circle is pi. Now the diameter of the circle drawn outside, around the outside of the square, touching its corners, is √2. So what then is the circumference of that circle? Well, it's √2 times pi. Okay, so the circle that is drawn outside the circle is √2 times pi, and then we can draw another square around that, and we can draw another square and circle, sorry, we can draw another circle. So we can draw circles and squares. So we started with a circle, we drew a square around it, we drew a circle around it, we drew a square around it, circle, square, and we can keep going like that. And we get these series, which we've, geometric series, which we have started on the right side here. So with the sides going up 1, √2, 2, 2, √2, going up by √2, and then the circumferences also going up by √2, and then the diagonals going up by √2 ratio themselves. Okay, circumference, of course, has a constant ratio of pi in it as well as the √2. So this is just giving a relationship between squares and circles, and we'll just look at the moment at this one here. Now, you can see that this is similar to what we were doing with the circles and squares, the condensed, the squares, where the square diagonal expansion, where we condense them so that we've got the first 3 squares in the series, diagonal side substitution, in the one square. So we've got the first one here, monad square, then we draw the square on the diagonal, and we get this one here, which is in a dynamic position, sitting on its point. And then we get the third one here. Now, notice how we've drawn a circle, just as we have been doing in this series. We've drawn a circle inside the outer square, but it's also outside the square that is standing on its point. Okay, so here we've got circle, square, circle, square, circle series. We've just got one stage in it. And we'll notice that the square inside the circle is half the area of the square outside. Now, we knew that from our earlier work, and we can remember that again by counting the triangles. So this square that is standing on its point has the 4 triangles here, and then notice that the square on the outside has an extra 4. 1, 2, 3, 4. And we knew that because this is the condensation of the geometric expansion of the square on the diagonal. Okay, so the square inscribed inside the circle is half the size of the square inscribed on the outside, or the square inscribed on the outside is double the square inscribed on the inside. Important ratio. And this ratio was, especially in the Renaissance, was considered quite interesting. And I know it's hard to see. I should have given a better diagram here on the right. Is a diagram of a famous villa that works with these squares and circles in its design. And Eric Timewell, in our last class, will talk more about the way this geometry was used in art and architecture in the Renaissance. Okay, now expansion keeps continuing, as I said, and here's a few more Renaissance pictures that are using squares and circles to look at the geometry of the human and relating that to the geometry of that they try to express the geometry of the human form in the geometry of the architecture, so in cathedrals and things like that. Now, as I said in our last class, session 6, Eric will give you more about that. Okay. Now, what I want to move on to here is to really emphasize that that this is all, squares are all about root 2. Okay, so if we look at this image here on the left, if we look at we've got our monad square down here in the corner, and it has the diagonal of root 2. Now, if we've got a double square, right, so we've just drawn a double square on by extending the sides up and across. So, and notice how that contains 4 squares within it. Its diagonal is root 2 times 2, right? So that's quite obvious, isn't it? So we've got another square up here with its diagonal of root 2, and we've got the square, original monad square. So it's been extended by root 2. And we go again to make a square 3 by 3, which will have these 9 squares here. 1, 2, 3, lines not drawn here, 4, 5, 6, 7, 8, and 9. The line's not drawn there, but we can see how the 3 by 3 square has an area of 9 and has a diagonal of 1, 2, 3 root 2s. So we've got side of 1, diagonal of root 2, side of 2, diagonal of 2 root 2, side of 3, diagonal of 3 root 2, and of course 4, diagonal of 4 root 2. So the diagonals are the sides times root 2. Okay, so the ratio is always root 2. Okay, So the ratio is 1 to root 2. So if there's 4 of them, it's 4 root 2. Okay, so it's always the same. Now, in a sense, every square has a diagonal of root 2. Okay, it's just the way we measure it, whether we use inches or, you know, lengths of our thumb or whatever else. It's just really the way we measure it. We can use centimeters, millimeters, whatever else, but the ratio will always be the same. So if you get away from your units of measure, then you can see that this root 2 is the principle, is a fundamental principle of square space. Okay. Now, we might ask, we will remember that the square that is 2 by 2 has a diagonal, according to Pythagoras' theorem, of root 8. So remember, 2 times 2 equals 4. So one of the sides is 4, the other side is square on on each side is 4. So 4 plus 4 equals 8. And then the diagonal is the square root of 8, according to Pythagoras' theorem. So in fact, you can show, and I've shown down the bottom there for those people into their mathematics, that actually the square root of 8 is equal to 2 root 2. And likewise, by Pythagoras' theorem, the 3 square, the diagonal is root 18, which is equal to 3 root 2. And for the 4 square, root 32 is equal to 4 root 2. So there's different ways of expressing these diagonals, but they mean the same thing. All right. So what I want to do now is show how length for width expansions work, because we're going to move into that with this final thing we're going to do with root 2, but also we'll be using this next week with the golden mean. So here we've got a square here. I've drawn it quite small because we're going to expand it. A special square actually, where the length, if you like, the longer side, is double the width. Okay, so it's we're starting with the basic. We're starting with a width of 1 and a length of double. So instead of doing diagonal for side substitution, we're doing length for width substitution. So here we've got a width of 1 and a length of 2. Now, if we make 2 the width, right, so the smaller side, let's just see that first. So we've got width of 1 and length of 2. Now, if we make 2 the width, then we double the length, we get the 4 square. Now, notice how the first square is pointing, if you like, east. Its length is to the east, and then the next square is to the south, right? So we've rotated anti-clockwise, if you like. Now, we've got a length of 4. What about we make 4 the width? Okay, so 4 is the width, and the length is 8. And then if the length is 8, and then the width is 8, then the length is 16. So see how we've gone from 1 to 2, and then 2 to 4, and then 4 to 8, and 8 to 16. And notice how we're rotating anti-clockwise. Okay. The first rectangle's lying on its side, if you like. Second one's pointing down, and the next one's pointing to the right, and then the next one's pointing upwards, if you like. And we can imagine a spiral here, so we will look at spirals shortly. Okay, so that is length for width substitution. All right. And that creates, and that is drawn on the, in this case, drawn on the double ratio. Because the original rectangle, it has a ratio between its width and its length of double. Okay. Now, what I did next in the class was we had a look at paper, and at standard paper we had A3 paper, and we were folding it and folding it again. So maybe I will just stop the video there. Sorry, stop the share screen, and you can have a look at me. So what we did was we got a piece of A3 paper actually, but we can start with A4, which is half the size, and we folded it over like that, just folded it in half, and then measured the length and the width, right? And folded in half again and measured the length and the width. Folded in half again, measured the length and the width. Now we'll notice with each fold, say we take that one here, the width, the shorter side there, pay attention to that, the shorter side there, when we fold it over, becomes the longer side in the new one. So we see the shorter side here, right, becomes the longer side in the new one, all right? And once again, the shorter side there, if we can still fold, becomes the longer side, all right? Okay, so what we found when we did those folds with A3 paper or A4 paper, it works just as well, just starting one stage later, is that the ratio between the width and the length is always the same. And in fact, it is √2. So I'll go back to sharing the screen again. Okay, so if we go to have a look at the design of this paper. So some of us might remember paper that had different ratios. For example, foolscap paper used to be used back in the 70s, maybe it went out in the 80s, not sure. But especially with printers, this new series came in, which has very handy qualities. And these qualities are related to √2. Okay, so in fact, so I'll just show you here, we've got A0 is the entire sheet here. So if you've done any, if you're a draftsperson, an engineer, an architect, or an artist, you'd be aware of these series. And some people work in A0. It's quite large. It's quite a large sheet to work with. A1 is perhaps more common for drawings, and then going down to A2 and A3. But A0 is the entire sheet, and then half of A0 is A1. And then we can see if this is A1 here, we can see drawn up here, A2 is half of that. So we've turned around, and half of A2 is A3, and half of A3 is A4. But each time the orientation has turned. So A4 to A5, A5 is half of A4, the orientation is turned, and so on as it goes down. All right, so let's have a look at how this works. So I've done it in reverse, so I hope that's not confusing, but we kind of have to do it that way. We can see here down in the width ratios that moving backwards, we are going in the root 2 geometric progression. So we're going from 1 to root 2. Root 2 times root 2 equals 2. 2 times root 2 equals 2 root 2. 2 root 2 times root 2 equals 4, and so forth. So we're just doing this in reverse. Okay. So if we start at 8 root 2, then the next one in the series is 8, right? And then the next one in the series is 4 root 2. Now notice how 4 root 2 is half of 8 root 2. That's why it works. Okay, so we've gone the ratio of the length to the side is root 2. Okay, so 8 times root 2 is 8 root 2. You go one more step in the series and the ratio is double. Remember, the ratio is double when you skip a stage. Okay, so if we're going down, we go from 8 to 4 to 2, or we go from, oh, I haven't got 8 root 2 in there, but we go 4 root 2, skip a stage, we go to 2 root 2 and 2 root 2. So we're halving every second step. So if the ratio of the length to the width is root 2, then when we get to the next, when we go down another step, the ratio is half. And so this allows us to get 2 pages in 2 pages in the previous page. So 2 A1s in A2, and then, oh, going the wrong way there, and then 2 A2s in A1 exactly. Okay, and then 2 A3s in A2 and 2 A4s in A3 as we go down the root 2 series. So all these pages that we use, including all these pages that we use, including, for example, our little postcard here, which I think is A6, right? So very common pages, that page sizes that we use are all expressing root 2. Okay. So we probably didn't know it when we pull out a page of A4 or print out a document that actually we are already working with this special ratio. So there we go. I think that's probably all I need to say here. Let me have a look. Yep. So that's enough for today. That's all the slides. After that, in our week 4 session, we moved on to the spiral of Theodorus. So next week, I'll give some bit of philosophical and geometric understanding of the spiral of Theodorus before we move into the golden ratio. Okay, so I hope that was helpful, and we'll see you next week. Okay, bye.